Hi, Year 11. I'm really sorry if it's really noisy in the background. The farmers in the fields next door, I don't know what they're doing, but you can hear it probably in the background, so apologies, but I want to make sure I get this to you at the weekend before your exam next week, so fingers crossed they stop soon. So these are some of the electromagnetic effects questions. This is the paper 7 on Save My Exams. I'll share the link in the video description anyway. So question 1 gives you 2 straight vertical wires, X and Y, passing through holes in a horizontal card. So this is looking directly down. So if you imagine a pencil is the wire, it's looking like this. So then it says there is a current in each wire in a downward direction. The magnetic field at Y, due to the current in X, so basically the magnetic field that X sets up, produces a force on Y. And then it asks you to tick a box for the direction of the magnetic field at point Y, and then the force that acts on point Y. So I'll zoom out just a little bit for a second. We're going to use our right hand grip rule. So it's your thumb pointing up and then your fingers curling round, and your thumb obviously represents your current direction. So if I were to point my thumb down through wire X, which is the thing that's setting up the magnetic field, you can see that you get a clockwise current going around X. So I can draw, not very well though, magnetic field lines. Obviously that should be more centralised, and we know that that will continually, oh, these circles are terrible, my goodness, sorry, it's a Saturday morning, I'm not in my teacher mode. So you get the idea though, we're going to have these circular fields, better circles than that, but we know that they're all going to be clockwise, okay? And so if I trace my pencil around, what I'm being asked to find is the direction of the magnetic field at point Y because of X. So I'm going to trace my pencil round along that circle, and when I get to point Y, hopefully you can see that it's pointing down the page. So you want to tick towards the bottom of the page for the magnetic field direction. Sorry, give me just a second. Hello. The dog has arrived. He wants to come and say hello. Right. Now we need to find the force then that acts on the current Y. So this is where we use our left hand rule, where we've got our thumb is our force, that's what we're trying to find. Our first finger is our magnetic field. We've just figured that out, that it's towards the bottom of the page, so it's acting down this way. And our current through Y is going down into the paper. So I'm going to point my middle finger into the page. I'm going to point my first finger down, and you can't quite see it, but my thumb is now pointing to the left. So the force on Y would be to the left there. So then it goes on to ask you to state and explain whether there is also a force on wire X. So quite straightforward. The first bit is yes. Let me grab a pen. So there is a force on X. And this time it's because wire Y sets up its own magnetic field. So if I were to draw that in a different colour, just to help you visualise what's going on, so it's so noisy. It's right hand grip rule again, so it's still clockwise because the current's going in the same direction. So if you imagine, X is also in Y's magnetic field, but for this one it would actually point up. But all you need to say for state and explain is that there is a force because of the magnetic field of Y. Okay, so then you can hopefully see I've got a diagram of a transformer. Let's see what I've got for you. Okie dokes. So you can see a DC supply being connected here. You've then got an iron core. you've then got a secondary coil here, and a galvanometer is just a fancy word for a really sensitive ammeter. So you can think of it as measuring the current. When the switch S is first closed, the needle of the galvanometer detects briefly, so you see a little current, but then at some point it then returns back to 0. So this is actually quite a difficult question. It's worth 3 marks. So the first thing you should have spotted really is that a DC supply is not typically used for transformers because we need that alternating current to have a changing magnetic field in order to get a voltage across here. If it's DC, oh my goodness, I might have to pause and wait because of the hammering. Oh my goodness, this has not turned out very well timing wise. If it's DC, as soon as the current is constant through this coil, the magnetic field is constant, and so you have a constant field on this side, and so you don't have a changing magnetic field. You're not cutting through field lines, so you don't get an induced voltage. So basically you only get a changing magnetic field at the very brief time where you close this switch and you go from 0 current up to its DC maximum supply. So there'll be a very short amount of time where there is that changing current and then changing magnetic field. But that very quickly stabilises, and at that point nothing's going to happen anymore. There's not going to be an induced voltage. So let's have a think about how we can explain this in 3 words. I'm going to pause while the hammering is going on, and maybe write it out and then I'll unpause. Okay, fingers crossed it's a little bit quieter. So what we want to say is that there will be a short amount of time where the current changes from 0 amps, so no current flowing, to whatever the DC current value is. So at the point where we close the switch, we go from 0 up to the current value. During this time, a changing magnetic field is then going to be cutting through the secondary coil. Okay, so once the switch is closed, we suddenly are going to have a magnetic field that is generated that will start to cut through this secondary coil. And this then causes an induced voltage very briefly, and a deflection is seen during this time. Hopefully that makes sense. But obviously as soon as that current value stabilises, you don't have a changing magnetic field. This would be constant, and then nothing will happen. There's no magnetic field lines being cut by the secondary coil, and you would get 0 again. Okay, so question 2. You've got a remote ski lodge receiving 18 kilowatts. I immediately would be writing 18,000 watts to myself before I get bogged down with the rest of the question. That's the power from a 120 volt supply. Calculate the current that the ski lodge draws. That's pretty straightforward. So you know that current is equal to power divided by voltage. But obviously if you forget to convert it to watts, you're going to get the wrong answer. And so you should get a current of 150 amps. Don't forget your unit. And then it asks you to find the electrical energy supplied to the ski lodge in 30 minutes. So we know that energy is equal to power multiplied by time. So we've got our 18,000 watts, but watts are joules per second. So we know that we need our time to be in seconds. So we've got our 30 minutes, and we know that each minute has 60 seconds. And once we plug that in, we get a value of 3.24 times 10 to the, let me count, 7 joules. So that's pretty straightforward so far. And just electricity stuff. It's only in part B that you start to see the electromagnetic stuff. So the power supplied to the ski lodge is from a nearby transformer that is connected to long distance transmission cables. The voltage of the transmission cables is much, much larger than that 120 volts. So it asks you for 3 marks to explain why the energy losses in the transmission cables are lower when the voltage is high. Okay, so for a given power supply, because this is important, So for a given power supply, a higher voltage requires a much smaller current. Okay, so we know that P is equal to IV. Power is equal to current times voltage. So for a given amount of power that we need to deliver, if we have a high voltage, we can have a much lower current. Okay, so that's the first thing we want to say. And we then want to say that current causes a heating effect. Okay, obviously, and a heating effect is going to be wasted energy. That's not helpful for us in the cables. Okay, so then therefore a lower current minimises the heat loss through the cables. That's not even saying for you, is it? Deary me, sorry. Okay, so make sure you've definitely got 3 distinct points there, okay? Let's have a little look at question 3. Alright, so this automatically looks like it's going to be asking you a little bit about electromagnetic induction. So we've got a bar magnet being pushed into a coil, a solenoid, and you've got a voltmeter connected across the ends of that coil. That centre 0 just means that the pointer rests at 0 and then it can deflect left or right. So it says, as the magnet is inserted into the left hand, the needle of the voltmeter deflects. Explain why the needle deflects as the magnet is inserted. So what we'll have is a changing magnetic field. Obviously the magnetic field of the bar magnet is like this, but as it moves in, it's changing its position within the coil, so you've got a changing magnetic field there. So you've got a changing magnetic field inside the coil, so that's worth 1 mark, and that induces an EMF or a voltage. Okay, so then it says state and explain the effect of inserting the magnet more slowly. Obviously the rate at which the field lines are being cut by the coil will have got smaller because it's being moved in slower, and so we know that from Faraday's law the EMF induced is proportional to the rate of cutting the field line. So if the rate goes down, the EMF will also go down, so we will see a smaller deflection will be shown. On the voltmeter. That's not going to get me 2 marks though, because I then want to explain why that is, because the rate of cutting field lines has got smaller. Sorry, I should have really printed this full size so I could actually get my answers in. So then it asks you to state what is observed when the magnet is withdrawn from the left hand end. So we've pushed it in and we're now pulling it back out again. So hopefully you can recognise that if the needle deflects one way when it goes in, it will deflect the other way when it is pulled out. So the deflection shown will be in the opposite direction. Alright, okay, so in part B you've got a transformer consists of a primary coil and a secondary coil on an iron core. An alternating voltage is connected to the primary coil. Describe and explain the operation of the transformer. So it might help you in the exam to sketch it out first so that you can really visualise what's going on. So if you've got your iron core and then you've got your primary coil and then your secondary coil, you can start to think about what's going on, can't you? So we know that we have to connect this bit up to an AC power supply. That's important in what we're thinking about because we have to have a changing magnetic field. So that's important because that then tells me something that I can write up here. And then this is obviously your output circuit that we connect things to. So we've got 4 marks, we're going to need 4 points. The first thing we're going to say is we have an alternating current in the primary coil. And if we didn't draw that, we might maybe miss that point, so always good to think about it. And this sets up an alternating magnetic field, okay, inside of the core. Okay, so this statement here is worth 2 marks because we're referencing that we have an alternating current setting up for the second mark the alternating magnetic field. Okay, so this field cuts through the secondary coil. 3rd mark. Okay, which induces an EMF in the secondary coil. Okay. So you always want to make sure that you can count 4 distinct points in your answer. And the time it took me to sketch that little diagram helped me recognise that I want to refer to the AC supply. Okay, so it's always helpful to do that. Let's have a look at number 4. This looks pretty straightforward. You've got the left-hand rule, which helps when describing the force on a current carrying conductor. So you then just need to fill in the other 2 boxes. So the first finger represents the field, or the magnetic field. And the second finger represents the current direction, worth 1 mark, easy peasy. In part B, you've got a simple DC motor connected to a battery and a switch. So it then asks you to label the 2 boxes that you can see there. So hopefully you can see that that is a brush. Okay, so this bit here, they're the brushes, and then that clearly looks like a ring that has been split in half. It is a split ring. Okay, you could say commutator as well, that would be fine. That's the more advanced word. Be careful, it is not a slip ring. They are very similar words. The ring has been split in half. It is a split ring in the DC motor. Slip rings, where they slip around, are for the AC generator. Okay, then on the next bit it asks you to state, sorry, we've already done this bit, right in the box is the part that the motor is connected to. We did that without even seeing the question. State which way the coil of the motor will rotate when the switch is closed when viewed from position X. So let's go back and have a little look at it. Rearrange just a little bit, sorry, 1 second. Okay, so you need to imagine that we are looking directly through X. So imagine our eye is here. Okay. The positive terminal of the battery is on the right, the negative on the left. So we know that the current is going to flow out of the positive terminal, through the brush, round through the wire, connected back to this side, round this way. Okay, so we need to have a think about what we know. We've got our field lines going from north to south. Okay, if we're looking through the slip ring, that's going to look like it's going from left to right. Okay, so our field is going from left to right when we look through here. Okay, then we need to think about the current direction. Okay, so I'm just going to highlight the two sides of the wire, the coil that's within the field. Okay, so we've got that side and we've got this side. Okay, and we know that the current will flow from the right hand side, so whichever section of the wire is on the right hand side, the current will be travelling that way, and on this side it will obviously come back round and the current will flow this way. Okay, so then we need to work out the direction of the force on each. So if we're looking through X, on the right hand side the current is travelling away from our eye. Okay, the field is going from left to right, so we're going to use our left hand rule. So we know we've got our field, I'll zoom out a little bit, we've got our field going from left to right, and our current would be going away from our eyes. So the force, you can't see it, my thumb is pointing down into the page. So I'm going to draw F this way. On the pink side, if I'm looking through the slip ring, the current looks like it's coming towards me. Okay, so my middle finger will point towards me, but my field is still going from left to right as I look through the slip ring. And so my thumb points up, the force on that side is up. Sorry, that's not very straight there, but you get the idea. So hopefully you can see then that that's going to cause a turning effect this way. Okay, which if we are looking through the slip ring, that's clockwise, as we are going round and round this way through our eyes. So you just want to say clockwise there. And then it asks you for two things. Sorry, it's very noisy. I'm bashing around here. Two things that can be done to increase the speed of the rotation of the coil. So there are quite a few things that you could say. An easy one is to increase the current from the battery. Okay, you could have more turns on the coil inside the field. Okay, you could use a stronger magnet. Obviously only give 2 in the exam. Don't list lots, because if you do that, the examiner won't give you the marks, because what you're basically saying is, here's a list, examiner, can you choose for me to give me the marks? So just make sure you only list 2. You could also include an iron core. So if you can remember 2 of those, that would be great. Alright, number 5, we're getting close to the end. I think we've got 2 more questions after this. So let's have a look. We've got 2 views of the same thing. So we've got a vertical wire cutting up through a piece of horizontal card. So Q is just above the wire, P is to the left, and it asks you to a little bit, draw a complete magnetic field line of force through P and indicate its direction with an arrow. So that's the first thing. I think this question is worded quite poorly actually. It's just asking you to draw the field line around the wire so that it cuts through P. So you're going to draw the whole circular field line so that it goes through P, and you can see that the wire is coming up out of the card. Okay, so the wire is coming up out of the page. So if I use my right hand grip rule and point my thumb up, my field lines are going to curl round anti-clockwise. Okay, so I just put those arrows on there. I've done 2, you only need 1. Draw an arrow through Q to indicate the direction in which a compass placed at Q would point. Okay, so the compass is going to line up with the magnetic field that it's been placed in. Okay, so it'll be influenced by that field. So it is going to be in the direction of the field at that point. So if I use my pencil again and go round and trace the tangent to the circle, at Q, which is directly above, my pencil points to the left. Okay, so the compass point will go to the left there. So just make sure that you've got that on there. You can actually do it directly through Q if that helps. So then it asks you underneath to state the effect on the direction that compass Q will point if we increase the current in the wire. That will not do anything, okay? All it will do is strengthen the field, so there'll just be more field lines. So it'll be a stronger field, but the direction it will be the same. So increasing the current has no effect. Okay, but if we reverse the direction of the current, think about our right hand grip rule, instead of going this way, we're now pointing down. My field lines have switched to be in the other direction. Okay, so in this case we're just going to say the direction of the field reverses. Or goes in the opposite direction would be fine as well. Okay. Then in part C, we've got the view from another vertical wire carrying a current up through the card. A centimetre grid is marked on the card. Right, so W is 1 centimetre vertically above the top surface of the card. State the magnetic field strength at S, T and W in terms of the magnetic field strength at R. You can use weaker, same strength or stronger, so it even tells you what words to put there. Okay, so let's have a little look. We can see that W, R and T are the same distance from the wire. Okay, they're each 1 centimetre away. Okay, so that field line will be going round the wire. It will be part of the same field line. It's at the same strength at R, T and W. So we're going to use same strength for T and same strength for W. Okay, so don't get tricked by the fact that there are 3 options given in the question. That's just how you can choose to describe them. You can have multiple being exactly the same. Okay, but S is much closer to the wire than R, T and W. Okay, and the closer you are to the current carrying wire, the stronger the field. Okay, so you want to say here it's going to be stronger. Because if you think about the radial field, if that's the wire, very close to the wire you have lots of field lines, but as you get further away, those field lines, oh dear, that's not very good drawing, is it? Ooh, but you get the idea. The distance between the field lines gets bigger the further away you go, and that shows that the field is getting weaker. So the closer you are, that's the stronger that field. Excuse the terrible drawing. Okay, are we on to the last question? No, 2 more. Oh my goodness me. Okay, so we've got an arrangement used to make an electromagnet or a permanent magnet. So we've got a cardboard tube wrapped around that we have turns of copper wire. You can hopefully see we've got a variable resistor connected in series to a 12 volt supply and then an ammeter measuring the current. And then it says 2 bars of the same size are also available, one made of iron and the other made of steel. State which bar should be used to make a permanent magnet. Okay, we know that steel is a hard magnetic material, so once it has been magnetised, it is very difficult to unmagnetise it, and so steel would be good for a permanent magnet, whereas iron is soft. Iron's better for the electromagnet. So, describe how the apparatus would be used to make a permanent magnet. Let's look back up here. So, we've got a cardboard tube, which means that we can actually insert a piece of steel inside. And what we can do is once it has been placed inside and it's settled, we can then switch the supply on. That current sets up a magnetic field that the steel will align with. Leave it for a bit, then switch it off. We have to switch it off first before we pull the steel out. Otherwise, we will undo all of the work we've just done in magnetizing the steel. Okay, so describe how we would use it. We would place the steel inside of the tube. We would then switch the DC supply on and leave a while. That's only 2 marks, it's worth 3, so we need to be careful. Actually, that's not true, sorry, I'm a big fibber. This whole thing is worth 3, that's 1, that's 1, that's 1. So place the steel wire inside the tube, switch the DC supply and leave for a while, and then switch off. Okay, before removing the tube. So we want to make sure we're saying switch it on, leave it, switch it off. Okay, then remove the steel. I'll have this in, squeeze it in here. We don't remove the steel until we've switched it off. Suggest why, one reason why the circuit contains an ammeter and a variable resistor. So the ammeter allows us to measure the current, and then the variable resistor allows us to then adapt it and control it if we need it to stop it from overheating. Okay, so to measure and control the current. To prevent overheating. Okay. During the making of a permanent magnet, the ammeter reads a steady current of 4 amps through the 5 seconds that the current is switched on. The voltage of the supply is 12 volts. So firstly, it's asking for the circuit resistance. So we know that resistance is voltage divided by current. So we're just doing 12 over 4 there, which gives me 3 ohms. Don't forget your unit. The power of the supply, P is equal to IV. These are really quite straightforward. So this time you're just doing your 4 amps multiplied by your 12 gives me 48 watts. Again, don't forget your unit. And then it asks for the energy supplied during the 5 seconds. So we know that energy is equal to power multiplied by time. So we're taking our 48 watts that we've just calculated and we're multiplying it by the 5. If you get a different value, you'll get a carried error. So just always carry on all the way to the end. Okay, so if you forget how to do an earlier bit, make up a number and use it later. Let's have a look. What do we have here? So we've got a 200 and we've got a 40. So 240 joules. Again, don't forget your unit. Okay. The potential difference across the variable resistor is 7 volts and that across the ammeter is 0. Calculate the potential difference across the magnetizing coil. Alright, let's have a little look. Back at the picture, that'll help us. So, we were just told, and I've immediately forgotten the number, which is not very helpful, that we have 7 volts across the variable resistor. This is a series circuit, so if 12 volts is the gain of energy per unit charge across the supply, that then has to be transferred across the circuit. So the sum of the voltages has to equal 12. So clearly we're going to have 5 volts across the copper wire, because 7 plus 5 is 12. Okay, so we're just going to say here 12 minus 7 gives me 5 volts. Is my answer for this bit. Sorry, very wonky here. State the general principle used in making this calculation. So in a series circuit, bear with me, someone's just coming to the door. Okay, back to it, sorry, I've had to pause, get rid of my intruders. I will carry on. So what were we doing? The general principle used to help us make this calculation. So we say in a series circuit, the sum of the voltages across the components is equal to the voltage supplied by the power supply. Okay. So you're basically just explaining how you need to do that calculation. Alright, we're finally on to the last question. Sorry, this has been a very chaotic recording. So, we've got a long straight wire between the poles of a permanent magnet. We've got that connected to a switch, which is then connected to a battery. So, when the switch is closed, there's a steady current in the wire. Okay, state the direction of the magnetic field between the poles of the magnet. Okay, well that's going to be from north to south. Okay, that's just directly across. I would try to refer to the things you're told in the question rather than left to right, but you probably would get the mark for left to right as well. The wire is free to move. The current is switched on so that its direction is into the page. State the direction of movement of the wire. Okay, so we've got a left-hand rule again here. So we know in our left-hand rule, our first finger is our field. That's going from north to south. My current is into the page, so my middle finger points down. That then leads to my thumb pointing down the page. Sorry, I'm using the word down too many times. Field, left to right. Middle finger, current, into the page, so away from the screen that you're seeing right now. Thumb downwards. Okay, so I can put F as vertically down here. So when you are referring to this, you're going to say vertically down the page. Okay, that's as clear as you can make it. And then you have to explain how you got that answer. Clearly I used Fleming's left-hand rule. Okay, so I'm going to say Fleming's left-hand rule was used. And I'm going to go one step further because this whole thing is worth 4 marks and I do not have 4 marks worth of stuff here. So I'm going to explain what each finger represents. So you're going to say your thumb is the direction of the force. First finger is field direction and middle finger is current. So I'm just giving that little bit of extra information to hopefully get that 4th mark there. Last bit of the video. Goodness me, if you've got this far, my hat is off to you because this is long. This experiment is the basis of an electric motor. Describe 2 changes to the arrangement shown that would enable continuous rotation to take place. Okay, so in this case we only have a single wire. The easiest thing you can do for yourself when you are thinking about what change we can make to make this continually rotate is think about what a DC motor looks like. And what we know is we have our field, our north and our south. We know that we have a coil of wire within that, okay, and we know that they are connected to slip rings, okay. And so if we think about how this looks different, instead of a single wire, we make the wire a coil instead. And then we can connect each end of the coil to a split ring. Okay, they're going to be the best things that you can say there. So change the single wire to be a coil of wire in the field. And then the second thing we can do, sorry it's terrible handwriting, is connect the ends of the coil to a split ring commutator. So my advice would be always sketch things out to help you get to your answer, because it could be quite hard to think about what to do otherwise. Hopefully that has been helpful.